All right, let's try this one. We're asked, does a precipitate form if we mix 3.5 milligrams of sodium chloride into a quarter of a liter of a solution? I like to draw a picture when I'm a little bit confused about what's going on. So I've got my quarter of a liter solution, and if I look carefully at what's in that solution, it's 0.12 mole per liter of a lead salt. Okay, so we have PbNO3, 2, and of course, probably know we call that what? Lead nitrate. Now, if you remember back to your solubility rules, one of the ones that you probably learned is that all nitrates are soluble. Okay, so to be honest with you, when I saw that was lead nitrate, I said, oh, it's a soluble lead salt. And in fact, when chemists want to make solutions of metals, which are sometimes tricky to dissolve, like lead, silver, things the like, we usually buy the nitrate salt, or maybe the acetate salt. But nitrate's very common. And we use that because all of these nitrate salts are soluble. It's very convenient. You can make solutions out of heavy metal ions, such as lead in this case, okay? So we're taking the lead nitrate, we're going to make an aqueous solution of it. Because it's soluble, we can get this lead ion into solution. So what we're going to do is we're taking that solution into the beaker. We are going to add 3.5 milligrams of table salt, NaCl. We want to know if a precipitate forms. The KSP for a sparingly soluble salt, which might form from these reagents, is 1.6 times 10 to the minus 5. Now, we haven't identified that yet, so I guess our first trick is identifying, well, what might happen. Now, I see lead 2 plus as one of my ions here. And I key on that right away because a lot of lead ionic compounds are not so soluble. Now, lead nitrate is soluble, so that's not a worry here. It's going to dissolve and we're going to be able to make a solution. But I'm mixing my lead nitrate with something else, aren't I? I'm mixing it with sodium chloride. So remember, precipitation reactions proceed by ions cross-reacting. So couldn't the chloride anion react with the lead? And of course, I'm kind of writing this in the backwards direction as the way the reaction might proceed, okay? But surely we could make some lead 2 chloride from the precipitation reaction of the chloride ion with the lead. And that's the key solubility equilibrium here. Now the KSP of the lead chloride, I looked it up in a table, it's right about 1.6 times 10 to the minus 5. That's the KSP for this stuff, okay? And basically what we're asked is, if we do this experiment, will this solid form or will it not? And the key bit of information that we need to figure out are what are the ion concentrations that exist in the solution when we mix them. So let's think about the lead first. This one should be pretty easy to come by. The reason why is because we have this solution, it's a quarter of a liter, and in that solution is 0.12 mole per liter of the salt. Now, when this salt dissolves, we get 2 copies of the nitrate, but we only get 1 copy of the lead. So as a result, my expected lead 2 plus concentration before anything happens should be about 0.12 mole per liter. That's how much should be in the solution. Now what about the other reactant, potential reactant, which is chloride? Can we figure out the concentration of the chloride in this solution once the mixing occurs? I mean, after all, we know what mass sodium chloride we added in, 3.5 milligrams. Maybe we could figure out the molarity of the chloride ion. That's going to be an important strategy here. So to do that, I got to figure out how many moles of NaCl I added. Now, I added 3.5 milligrams, which is what, 0.0035 grams? I have to divide by 1,000 to convert to grams. If I look up in a data table what the molecular weight of sodium chloride is, I find that it's 58.44 grams per mole. So the gram units cancel, and we have moles basically once we do the math. So it looks like I need to do that math. So I need to do 0.0035 or 3.5 milligrams. Divide that by 58.44. And when I do the math, the number of moles of NaCl I get is 102034000005989. And that's in mole units. Specifically, moles of sodium chloride. Now we've got to do some stoichiometry. We know from the formula of sodium chloride that we get 1 chloride ion for every mole of the salt. So this also corresponds to how many moles of chloride I've placed in the solution. Now it's not the molarity, it's moles. So it stands to reason then that I could compute the molarity of my chloride by taking that number of moles and dividing by the liters of solution. That's what I'm going to do. So I'm going to take 5.989 times 10 to the minus 1, 2, 3, 4, 5. That's my moles, and I'm going to divide by the total volume of solution. Now I read this problem again. It seems like the initial volume was 0.25 liters, and I just add a tiny little pinch of sodium chloride in there. Probably not going to change the volume all that much. So I'm going to use that initial volume as my final volume as well. And I'm going to take my number of moles, and I'm going to divide it by 0.25. It's essentially like multiplying by 4. And when I did that, I find that the initial molarity of the chloride is 0.0002395 mole per liter. Well, that's a molarity, isn't it? Now that I've solved for the molarity of the chloride and the molarity of the lead, I can start to assess whether or not a precipitate will form in this solution. The way to do that is to solve for the reaction quotient. In this case, we call that QSP. Remember, it tells us which direction our equilibrium will shift. And just like the QSP of previous chapters, it's really just the same as the equilibrium constant expression in terms of how we set this up. Got to square the chloride. But what we put into these brackets are not the equilibrium concentrations. However, they are the initial concentrations. So for instance, my initial concentration of my lead is 0.12, and my initial concentration of the chloride, which I need to square, is 0.0002395. Run out of space. I'm going to have to erase this and write it again. Like I said, I got to square that one, right? And that's what we're going to do. So let's see, I got to find the right button for that. All right, I think I succeeded on my calculator. I got to multiply that by 0.12. And I get 7 times 10 to the minus 1, 2, 3, 4, 5, 6, 9, I think. That's my value for QSP. 369. Yes, 7 times 10 to the minus 9. That's my QSP. Now the next question is what in the world do I do with that? Well, what we do with it is we compare it with the magnitude of the value of our KSP. Is QSP bigger, smaller, or equal to our KSP? We've got to think about that for a second, right? So I think in this case, it looks like my QSP is substantially smaller than my KSP, isn't it? This is 10 to the minus 9th, and my KSP was what? 10 to the minus 5. These are the numbers that I'm comparing. So because QSP is so much smaller, what that tells me is no precipitate will form here. I'm not expecting to get a precipitate. In other words, My lead chloride salt is soluble enough, as described by its equilibrium constant for dissolution. It's soluble enough to support these concentrations of these ions in the solution. And that's that, no precipitate. Now, if QSP was greater than KSP, if that was true, the reverse would occur and a precipitate would be expected to form. But not in this case.